So, today's topic is C60, that is a 60 atom carbon molecule named, a very long name, Buckminsterfullerene. So, we will look at the structure of Buckminsterfullerene. So, we have already discussed allotropes of carbon, we are discussing that topic, and we have discussed graphite, diamond, graphene and carbon nanotubes. So, this is the last topic in the allotropes of carbon which we will discuss now, and that is Buckminsterfullerene, discovered in 1985. The discovery was reported by a article titled C60 Buckminsterfullerene. So, a new molecule was discovered by these authors Crotto, Heath, Bryan, Curl and Smalley, and they published their report in a very famous journal called Nature. In 1985, a very short article, you can see only 2 pages, 162 to 163, and the title of the paper was C60 Buckminsterfullerene. Actually, their interest was in long chain carbon molecules in interstellar space, and they were trying to replicate some of these in their laboratory experiments by evaporating graphite by laser. And in this kind of experiment, they came across this new molecule, 60 atom molecule, the structure of which they solved and gave a name Buckminsterfullerene. For this achievement, they were awarded 1996 Nobel Prize. Buckminsterfullerene, of course, a very long name. So, shorter names like fullerene or buckyball is also common for this molecule. So, let us now look at the structure of this fullerene or buckyball. To get this structure, we have to be familiar with a solid called truncated icosahedron. To understand truncated icosahedron, let us look at icosahedron. Icosahedron, shown here, is one of the Platonic solids or regular solids. I will have a separate discussion on Platonic solids for you. For the moment, let us just look at this icosahedron. It has 12 vertices or 12 corners, 30 edges, 30 such edges, and 20 equilateral triangles. So, all edges are equal, all vertices are identical, that 5 equilateral triangles meet there, and all faces are identical equilateral triangles. This is a beautiful solid and is known as an icosahedron. Now, in fact, the icosahedron word comes from its 20 faces. 20 is icosa and hedron is faces. So, it is a 20 faced solid, it is a 20 faced regular or Platonic solid. Now, to get to the structure of C60, we have to truncate this icosahedron. By truncation, we mean cutting off or chopping off the vertices. Let us see how we do that. So, I make a small pentagon here. So, this around this vertex, I have now a small pentagonal pyramid, and I just chop off this pyramid to get a pentagonal face. So, the pyramid has been chopped off, and instead of the vertex of icosahedron, I now have 5 new vertices and the corners of this pentagon and a pentagonal face. I do this operation for all other vertices. So, if I chop off the second vertex there, I again get a pentagon, and if I chop off this top vertex, I again get a pentagon there. The chopping is done in a way that what remains of the original triangular face is now a regular hexagon. So, you can see that if I chop off all the 12 vertices of icosahedron, I will get 12 pentagonal faces, and there will also be hexagonal faces corresponding to the original 20 triangular faces. So, I then get a truncated icosahedron which is shown here. So, you can have these, you can see these 12 pentagonal faces. Total face now is 32, out of which 12 is pentagonal and 20 is hexagonal. So, the structure is not that difficult once you come from icosahedron and then truncated icosahedron. If you are still facing difficulty, all you have to do is to just look at a football. So, the makers of football have already solved this problem. The football is nothing but a structure made of hexagons, the yellow hexagons in my football here, and the black pentagons and the black pentagons. And you can see that there are 12 such pentagons and 20 hexagons in a football. So, if you examine a football carefully, you will get these numbers directly from the football. So, a football is nothing but a truncated icosahedron. So, if you look at the football, you get the structure of C60 molecule, that in the truncated icosahedron, I have probably not yet mentioned that in the truncated icosahedron, now you should imagine a carbon atom sitting at each of these vertices. So, that is how there are 60 vertices and you get 60 carbon atoms sitting at each of the vertices of a truncated icosahedron. So, that is the structure of the molecule, a very solid molecule. Carbon valencies are all satisfied, because you have for every carbon atom, you can see there are 3 edges that corresponds to 3 bonds, but 2 of them are single bond and 1 of them is the double bond. So, the 4 valency of carbon is satisfied in the molecule. It is a very nice solid molecule, very strong, but still this is just a molecule. So, this is the football picture, and I have already shown you the real football. You imagine a carbon atom sitting at each of these vertices and you get a nice C60 molecule. Now, this is just a molecule. If you crystallize it, one of the forms of the crystal, C60 crystal, is made up of these molecules, and as we know that every crystal can be written in terms of a lattice and motif, and it turns out that the lattice of C60 is a face centered cubic lattice, and the motif is 60 atom fullerene molecule sitting at each lattice point. So, the centroid of the C60 molecule coincides with the lattice. So, the carbon atom do not actually sit on the lattice points, they are distributed around the lattice point, but they are associated with that lattice point. Let me draw that and show it to you. So, if I can now draw an Fcc unit cell. You are familiar with Fcc unit cell. So, we begin with a cube and we place lattice points at each of the corners and at the 6 face centers. So, all these little crosses are lattice points, and if I now think in terms of the C60 solid or a C60 crystal, so I place the C60 molecule, the truncated icosahedron molecule, at each of the lattice points. Now, I will have difficulty drawing, you can understand, the C60 molecule exactly. So, I just draw a sphere and write C60 inside that to represent that it is not a single atom, but a 60 atom So, I keep placing at each of these lattice point a 60 atom molecule. The centroid of the molecule coincides with the lattice point, but the carbon atoms do not coincide with the lattice point. They are distributed around that lattice point as truncated icosahedron. All of these are C60. So, you can see the structure is very different from the structure of the cubic close packed structure, where each of these spheres would have been a single atom. So, the CCP structure and the C60 solid share the same lattice, but they are still very different crystal structure because their motifs are very different. CCP has a single atom motif. So, CCP, if I write that down for you, CCP also FCC lattice, but the motif is one atom at each lattice point, one atom at the lattice point, and a C60 solid you have the same lattice FCC lattice, but now the motif is of 60 atoms. So, motif, although lattice can be only one of those 14 Bravais lattices which we have discussed, motif can be quite complicated, and this is one of the examples which we have, where a 60 atom carbon molecule, the fullerene molecule, is being used as motif on an FCC lattice. The name fullerene, it comes from an American polymath named Buckminsterfuller. So, I show him there, a very famous American architect, author, designer, inventor. He was a polymath. He excelled in many different fields, although he never graduated from Harvard University, where he went to study, and was expelled twice during his stay here, and you can see the reasons, once for spending all his money in partying and another for irresponsibility and lack of interest. So, if any such accusation is there by your university on you, do not feel disheartened, you are in good company. But why the molecule was named Buckminsterfuller? He was famous for designing so called geodesic domes, show you here, such one example, the Montreal Biosphere in Montreal, designed by Buckminsterfuller, and you can see it is a huge dome made up of hexagons, and possibly you will have to find pentagons also, because a lattice grid of only hexagons will always be flat. You require pentagons to curve them. So, somewhere in this geodesic dome, I can see hexagons here, but somewhere in this geodesic dome you should be able to find pentagons also, otherwise the structure will not be curved. So, because the authors, the original authors who got the Nobel Prize for discovering C60 molecule, when they were trying to solve this structure, they recalled the geodesic domes made by Buckminsterfuller, and to honor him they named the molecule Buckminsterfullerene. So, with this, thank you very much. We have finished the carbon structure. I will have one lecture on the structure of solids itself, particularly the platonic solids or regular solids, because you have seen tetrahedron, cube and octahedron in while discussing crystallography, and now in C60 molecule you have met another one which is icosahedron. So, I think I will give a general discussion on this in another video.